Bishop & Associates is a market research firm specifically for the electronic connector industry. And we've been doing this for about 35 years now. And we're finding that the industry is a subset of all the electronic component industry, of course. But it's for instance, in 2016, it was a $52 billion business. So it's not insignificant. It is top-heavy in the sense that the top 10 manufacturers listed there represent over 60% of the total business that was booked that last year. There's actually another thing that's interesting about this. This chart used to be dominated by companies based in North America. And now we're down to about the top 4. And the rest of them are all based in Asia. And of course, what that represents is the fact that so much electronic manufacturing has moved there, and now these companies, 6 through 10, pretty much are part of the local supply chain. So things are changing for sure from a business perspective. Actually, we track over 750 connector manufacturers around the world. But you can see many of them are tiny and they're very specialized. So what are the trends affecting connectors? The same trends that you're seeing at the board level and at the system level. Smaller, faster, and cheaper. So back in 1956, the RAMAC 3, it was the IBM RAMAC 350 system, was a disk storage system. It consisted of 50 hard disks, each one 2 feet in diameter, and the total capacity was 5 megabits. So about a month ago, Kingston Electronics introduced a pocket flash drive, and that flash drive has 2 terabits of capacity. So it's an incredible compression of capacity and cost. On the far side there is the Freescale. They make a microcontroller. It's a 32-bit controller. Its dimensions is 2 millimeter by 1.6 millimeter. So it's just amazing, and the trend continues. So how is it affecting connectors? Well, essentially in the same ways. Connectors have to be smaller and faster and cheaper. When a connector is specified by a standard, for instance, PCIe, it started out at 2.5 gigatransfers per second. The new one, which is PCIe 4.0, is expected to operate at 16 gigatransfers, and the connector will be the same. Backward compatibility is a hallmark of that. Same thing has happened to a large degree with the universal serial bus. But we'll talk a little bit more about how that's actually being accomplished. So one of the areas that's most obvious of where you're seeing smaller and faster going on is in the I/O panel. Now, I spend most of my time in the computing and telecommunications marketplace. And in those areas, a server or a switch is in a 1U chassis. And so the I/O panel is tiny. And yet they're trying to push terabits of information in and out of that panel. And so it's essential that that not become a data bottleneck. So the small form factor pluggable module has been very well accepted, and it's evolved. It started out as the SFP at 1 gigabit in one channel. Then it went to SFP 10, or SFP plus, I mean, with 10 gig. And then now it's up to 28 gig. Same thing happened with a quad QSFP, 4 channels, 1, 10, and then 28. But even that isn't sufficient. So recently, TE Connectivity came out with a micro QSFP. It offers 4 channels of 28 gig in an envelope about the size of a standard SFP. So it continues to shrink and increase the capacity. There is also an MSA for the double density QSFP, which will be 28 gigs times 8 channels to support 200 gigabit applications. And at the same time, as mentioned earlier, you can't forget about cost. So for those applications that are specific, that do not need a long run, and do not need an optical option, there is an MSA called the RCX configuration that is a copper-only, less than 3 meter link that is optimized for low cost. So the connector industry is trying to respond to these demands of faster, smaller, and cheaper in whatever ways it is available, and it continues. Same thing is happening in the backplane area. They demonstrated 56 gig in a backplane copper connector system. There's a number of ways of getting there, but obviously at 56 gigs, the channel gets very, very short. The faster the bandwidth, the shorter the length is going to be because of signal integrity issues. So one of the things that people are considering is going from non-return to zero signaling to PAM4 signaling, which essentially doubles the throughput per clock cycle. So if an engineer is faced with wanting a 25 gig channel, essentially, he can actually design a 12.5 gig physical system and get the throughput of 25 gig. It keeps him in his more comfort zone, at least for the time being. It's not trivial to design a 25 gig channel today. So we're seeing more and more interest in PAM4. And finally, are we reaching a practical limit of copper? It's a question that's been asked for probably 20 years now, and there's no real good answer. There are new ways of making copper work, but they're becoming more expensive, they draw more power, and they consume more space. So at some point in time, physics will dictate that optics will be more attractive and probably the only option. But at least for the short term, copper will remain to be probably the dominant connector system. In the short term, designers are trying to figure out how to maintain very short channel links between daughter cards or line cards. And there's three options. Actually, four high-speed backplane connector manufacturers, in addition to the traditional backplane design, offer these options. The first one is an orthogonal connector, and it's an orthogonal midplane, actually. And so you have daughter cards plugging 90 degrees to each other on the front and back side of the midplane. And it's a very short path. There's a very little short electrical path on the backplane itself, so you end up with very little degradation due to the backplane. And the problem is you've got two different zones now for cooling. So there's advantages and disadvantages. So one way to solve that problem is just eliminate the midplane entirely. So there is a orthogonal midplane, a direct configuration, that the connectors actually have a gathering mechanism built into them so that they allow daughter cards to mate directly to each other orthogonally. And in those cases where you have a very large system and you're going to have long channels, another option is to go to a cable backplane. So rather than injecting your high-speed signals into the backplane, you transition them to discrete shielded differential pair, where you can control the impedance, you can control isolation from noise and crosstalk much better. So it's an expensive way to go. It does solve the problem of laying out that backplane, which can be very expensive, many layers, difficult, and it has to use very expensive material. But I cannot imagine trying to find an intermittent contact in a rat's nest of cable. But it is an option, and it's being used. So there are options of getting there. Same thing's going on with mezzanine connectors. We're seeing more and more mezzanine connectors that are optimized specifically for high-speed differential signaling. And we're also seeing interest in hybrid mezzanine connectors that combine power, low-speed signals, and high-speed signals all in the same housing. It really simplifies mating two parallel boards because now you only have one connector to mate, and there are pre-alignment mechanisms built into it, as opposed to having three separate connectors that all have to mate simultaneously. So there are some advantages to that design. Okay, we're also seeing new mezzanine connectors enter. This is an addition that TE recently introduced. It's called the MultiGig. It's part of the MultiGig VPX family, and it's essentially a double-ended, a double-sided compliant pin hitter. And so you essentially nail two parallel printed circuit boards together. It's pretty much a permanent connection system. It's simply press fit. It's a very low profile, only 4 millimeters. They're end stackable, so you can create whatever pin count you need. And it's rated to 10 gig. So they continue to try to respond to customer requirements for stacking. So how are connectors migrating from relatively low speed to some of these 25 and even 50 gigabit applications? And it's been a continuing process. I kind of call it bandwidth creep, because a connector that had originally been introduced at a 5 or 6 gigabit range all of a sudden changes its rating to 10 or 12. And a lot of work has been done to these connectors to be able to achieve that. Certainly they've controlled the impedance that much more tightly by analyzing every millimeter of circuit length through the connector body, looking at every dielectric, both air as well as plastic, looking for any kind of discontinuities that can cause reflections and bumps. if you look at a TDR of a signal passing through the connector, it's almost perfectly flat now. What we have found is that it's actually the printed circuit board launch that is a greater source of noise. So consequently, the connector companies have made a lot of changes in that area, including making the compliant pins smaller, which means the plated through hole barrels can be smaller, which reduces some of the crosstalk. Certainly the stubs in the back have to be back drilled to eliminate that. We're going to more ground pins and staggered footprints to the point where you essentially are creating shielded differential pairs right into the printed circuit board itself. And then finally, the use of high performance material like Mectron 6 is mandatory if you're dealing with a 25 gig channel. So that's how we're able to get to some of these extended speeds. Same thing with power. We heard from several other speakers that power is a big issue, and consequently the thermal issues get aggravated the smaller the envelope becomes and the greater the amount of power. So again, connector companies are responding by improving the contact designs themselves. In some cases, they have made them more redundant so that they're more shock and vibration resistant. They've gone to some pretty exotic copper alloys that get closer to the conductivity of pure copper. They still have the spring characteristics that are necessary, but there's less loss. So the bottom line is the contact can deliver more power to the load, and it also doesn't generate heat. And of course, you don't want any more heat being generated in the system than you possibly can get away with. So that's very desirable. Power connectors now are low profile, basically so that they don't obstruct the cooling airflow. So that's a major change. And in some cases, they've actually cored out the connector housing so that air is designed to go through it and circulate it around the contacts. And we've already seen some companies that have offered that they can raise the contact current rating by 10 or 15% simply by allowing a controlled amount of air circulating through the contacts themselves. And then finally, we're starting to see connectors with an integrated heat sink. Rather than refer a customer to a third-party heatsink that would be a strap-on that may or may not be really efficient, in some cases they're starting to design heat sinks into the connector body itself so it's designed specifically for that application and is ultimately more efficient. So we can't talk about connectors without talking about optical interfaces. And optical cables, as was mentioned earlier today, are ideal when you've got a standard, but the application calls for a length much longer than what the standard permits. So you plug an active optical cable at both ends into the electrical interface, and you can go 3, 4, 5 times the distance because your signal is being conducted optically. Pluggable I/O, we spoke about that, the QSFP, QSFP plus, 28, and all the different variations. There's actually a whole alphabet of pluggable connectors that have been designed for both short and long distance applications. Optical backplanes, not like Mike was talking about. When I'm talking about optical backplanes, I'm talking about a backplane with a optically conductive layer integrated into the backplane itself. And that pretty much still remains a laboratory oddity. There's been a lot of development work, a lot of concepts, but very little practical application of a true optical backplane. I think we're waiting at this point in time for advances in silicon photonics, and perhaps when we get to true optical computing, where an optical backplane will make the most sense. Still continued work going on in that area, but at this point, not much in the way of actual production. And finally, midboard optical transceivers. We heard earlier presentation about those, and they've been around for 15 or 20 years. And about 3 or 4 years ago, the large connector manufacturers, the FCI Electronics, Molex, the TE Connectivity, all jumped on this bandwagon of a transceiver for generally up to 12 channels, up to 25 gigabits, and it's a full duplex transceiver. So they all introduced their products, and actually Samtec was before them a little bit in the sense of coming out with this flyover concept, and that is the concept. The idea being you would mount a transceiver close to an active device like a SerDes or an ASIC, and rather than run those signals through the printed circuit board where they have to be very carefully controlled, you immediately transmit them to this transceiver, which converts it to an optical signal, and then the signals fly over the surface in an optical cable. So it could go to an I/O port, or it could even go to another part of the board. And so it's been very well accepted, actually. And Samtec now offers both a copper version, which they shield a differential pair, as well as a true optic version in a ribbon configuration. So as I mentioned, the other manufacturers, the big guys, decided to get into this marketplace. And since then, it's kind of gotten mixed. FCI was purchased by Amphenol, and so it now is in the Amphenol bag of products. It has not seen a whole lot of promotion. Molex introduced their product about 2 years ago. It was a full optical transceiver. They've withdrawn from the market. They are waiting for an industry standard to be developed. And there is work in that area in the process of it, but I've not seen a finalized standard at this point. And then finally, TE Connectivity offered their CoolBit connector. It was a full 25 gig times 12 channel transceiver, and that's been withdrawn completely. And the thinking there is that TE is really focusing on ruggedized connectors and on sensors. And so that's where their development effort is going at this point in time. So it seems like this flyover concept has a lot of merit. It's been utilized in embedded applications, and I think that we're going to see more and more involvement with it as time goes on. So what does a connector manufacturer have to do in order to have their products actually accepted? Well, it takes a lot of support. It's not easy to develop a reliable, first-time out 25 gig channel. So in order to support these high-speed products, all of the 4 or 5 connector manufacturers that offer these kinds of products offer a real roster of support mechanisms. 3D models, eye diagrams, evaluation printed circuit boards, reference footprints, which are very important now, S-parameter data, which is essential if you're going to be doing a full simulation of a channel. Online simulation tools are coming on very strongly now, in the sense that an engineer can get online, he can plug in the parameters of his proposed circuit, and it'll tell him how well it's going to play or not. Because the whole idea is to be able to get to a circuit that works the first time. You can't breadboard a 25 gig channel. So you really pretty much have to either have one fabricated, which takes a long time and is very expensive, and if you get it wrong, you have to do it again. So simulation is the way to go, and having these kinds of resources available is pretty much an essential requirement of being in this business. And it includes direct engineering support. Customers can call a TE or a Molex or an Amphenol and then go one-on-one with an engineer. So that's the kind of level of support that's required these days. So what's driving the market today? What we're seeing is, of course, the IoT, the industrial IoT, the commercial IoT. There are literally billions of devices that are scheduled to be connected to the internet. So I call it a Carl Sagan number because it's billions and billions. And it's going to continue. And it looks like this train is really headed, that's what's going to really happen. There have been a lot of talk about, are these real numbers? Is it really going to happen? It is going to happen. And it's going to impact cloud computing for sure. It's certainly going to impact automotive electronics because when you look at a car today, we have driver assist functions. And there's dozens of computers on a car today. When we get to full autonomous vehicles, it's going to be a whole different animal. So we see automotive electronics absolutely exploding. And it's going to change the nature of the connectors in automotive applications also. I think what we're going to be seeing is computer-type connectors in a car in an automotive environment, which means they're going to be smaller, they're going to be much, much faster, and in many cases they're going to be optical. The other thing is they must be more reliable because these connectors will be conveying information real time, and they're going to control steering and they're going to control braking. So it's life-reliant systems. So the reliability is going to be very, very important. Of course, industrial automation we see as being a major growth area, as is mobile electronics of all kinds. I mean, we talk about ubiquitous computing, it's global, and we see nothing but growth in that area. So what do we see in the future for emerging markets? These are markets that we see as something that's perhaps changing the world as we know it. Well, a true autonomous transportation has so many implications beyond just transportation, it's just amazing. Not only will cars talk to each other, but they'll also be talking to the highway infrastructure. So the traffic control systems will all be monitoring the traffic, and with a certain degree of intelligence, it'll make decisions as to what's the most efficient way of moving traffic. I know I was really looking forward to the point of not having to stop at a stoplight when there's no cross traffic. So we'll see. But the amount of electronics necessary to automate our traffic control systems in this country alone will be amazing. Wearable electronics, particularly in medical-related products, I think are going to be amazing. Additive manufacturing, it's almost too broad to cover, but the bottom line is there are 10 or 12 technologies and that they're additive, considered additive technologies. And there are brand new materials that are coming on almost every day, it seems like, that are compatible with these technologies. And so the advantage there is that you can build plastic toys and you can also build jet aircraft turbine fins using additive technology. So we see that as being a major area for more connectorization. Robotics, very exciting area. It used to be basically heavy industrial applications. Now we're seeing very low cost, very easy to program robotic arms that can do assembly very inexpensively. So we see that as being a growth area. I think it's interesting to me that the 6th largest manufacturer of connectors is based in China. They build all, well, they're based in Taiwan actually, but Foxconn builds all their products in China. Very low cost point of labor. They are the largest consumer of robotic assembly equipment in the world. So if they can justify robots to assemble connectors in China, it's going to be interesting to see what happens when we bring that kind of manufacturing capability here. So finally, there's cloud. We talked about cloud and fog computing. There's even another layer of bringing servers closer to the application and mist computing, another area of connectorization. And finally, artificial intelligence is an area we've hardly even scratched. It covers everything from the IBM Watson system, which does diagnostic medical analysis, to the Amazon Echo, which gives you voice access to the entire internet. So that's another area we see is just ripe for development. So the bottom line is when we try to come up with forecasts, we're not just looking for new products, we're looking for disruptive technologies. We're looking for technologies that could not only change the way things are done today, but perhaps destroy an existing market and replace an existing product. And it takes a lot of time. We talk to a lot of resources. And it's just good to know that when we need to do this, we need to talk to experts. And if we give Ray just a little bit of coaxing, he's always available to make his opinions known. So